Recording in progress. Alrighty. And I realized that I'm not quite sure where my recording is from yesterday. I'm hoping that it took. I'm wondering if I closed my computer a little too soon before it had finished converting, but we will see. I will put it up if it did get recorded. If not, I think everyone was here yesterday, so more of a problem for today, because I know a few people can't be here. So when last we left, we were looking at number 86, and I think we're doing 86 all the way through 94. So we have this system in which we have the copper and the chromium electrode, or sorry, the two copper electrodes. I'm just going to close the door so I don't disrupt people in the prep room, so just give me a second. So at the anode, are we oxidizing copper 2+, or are we, is that the anode? No, that's the cathode, because that's where the electrons are moving towards. There we go, there's our electrons. And so that's our cathode. And our electrons are traveling towards the positive. So that's our anode. And so we have copper. And we have, it could lose electrons. We have chloride, which could lose electrons. Oh yeah, here we go. Copper, which could lose electrons, chloride, which could lose electrons, or chromium that could lose electrons, or water that could lose electrons. That's what we came up with yesterday. Okay, so we have Cl minus H2O, Cu, and Cr2+. Let's go take a look at those four things. So losing electrons. So if we're losing electrons, we're going to be looking on the right-hand side, and we are going to be looking for chloride. So here is chloride. And we also wanted water. So here is water. Now, if we were just looking at the chloride and the water, we would say, because chloride is within the overpotential bracket, out of chloride and water, chloride wins. So now we're going to say, okay, it's not water that gets oxidized, it is chloride, because anything within the overpotential bracket ends over water, gets oxidized more easily than water. Oxidized more easily than water. Okay. And we were also looking for copper, Cu0, 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 Cu0. Now we have two coppers here. Okay. And, oh, not that one. That one. The oxidation potential going to copper 1, is negative 0.52 volts, and the oxidation potential for copper going to copper 2+ is negative 0.34 volts. And so of those two, the copper going to copper 2+ is preferred because it has a less negative oxidation potential. So it's not going to be this copper, it would be that copper. And going back, we are comparing with water and, or not water, chloride. Chloride, its oxidation potential is really not very good, negative 1.36 volts. And so chloride has been knocked out of the running. Even though it would win over water, it won't win over copper. Our last one that we are looking for is chromium 2+. Ooh, and it looks like we may have a winner, because chromium 2+ has an oxidation potential of positive. positive 0.41 volts. And so that would be better than the copper. So copper's been knocked out of the running because that is our best, our highest oxidation potential. So at the anode, chromium is going to go from chromium 2+ to chromium 3+. All right. So at the anode, well, I don't believe that it would stay the same. I think this is a bad question because the mass of the anode then should be staying the same because copper is not being oxidized at the anode. Chromium is being oxidized at the anode. I'm just going to say this is a bad question. Unless anyone out there has a genius look at this one and they're like, oh, hey, hi. Yeah, sorry, I've got a lesson going on. You can go in, yeah, absolutely, no worries. Okay, so where were you? Yeah, it's a bad question, so let's not worry about it too much, but let's just take a look at what would happen at the cathode. So we decided we could not find chromium. Oh yeah, this is just a bad question. Let's skip that one. But, you know, we went through the process of how we would figure it out, which is kind of useful. All right, which of the following are produced at the anode and the cathode during the electrolysis of aqueous? And remember, electrolysis is non-spontaneous. Potassium sulfate using carbon electrodes. So the carbon electrodes are inert. I don't know why this is floating around here. Anyway, that's okay. So we are looking at for possible oxidations. Always water. And if we're looking at oxidation, is it possible for K+ to get oxidized? Can K+ become K2+? And the answer is no, it can't. It does not want to lose a second electron because its second electron after it loses the first one is not on that outer shell anymore. It's on a new shell that's closer to the nucleus, on the next shell that's closer to the nucleus. So not K, let's take a look at SO4 and see if it can get oxidized. I think it can. So SO4 up here somewhere. Ah, there it is. SO4. Ooh, not very good at getting oxidized, especially when we compare it to water getting oxidized, which is here. And that would be negative 0.82 volts. So we are producing then oxygen and H+ at the anode. Maybe 4 and a 2. I'm not really balancing this. I'm not going to worry about it, but that looks not too bad. Maybe 4 electrons. Yeah, 4 electrons. I think the one on the chart is half of that, but that's okay. All right, so this one wins over sulfate. So what is being produced at the anode? Because of course, anode is where oxidation occurs. And that would be hydrogen. Did I do that right? Oxygen, O2. So when they say hydrogen, they mean H2. Otherwise, they would have said hydrogen ions, okay, H+. When they say oxygen, they mean O2, not O2-. And so we are looking at either C or D. And which of the following is produced at the cathode. So for our cathode, our possible reductions are, we have water, of course, and K can get reduced. It can gain an electron and become K solid. So let's compare our water and our potassium, and we'll also go and check and just see about SO4. I'm not sure if SO4 does get reduced, but we can look on our chart. Okay, so we have water getting reduced. That's down here. So water getting reduced is negative 0.41 volts, as opposed to potassium getting reduced, which is here, and that is negative 2.93 volts. So definitely water instead of potassium. Let's just go double check and see if there's no sulfur. If there was any, it would be sort of hanging around the top part of the table, but I think it's on only, oh, it is there. However, do you see something there that means that we cannot use that reaction for sulfur? Not in the conditions described in the question. Hopefully, you notice there's another reactant. There is hydrogen. Yes, exactly. And so we would need this to be acidified. And nowhere in the question does it say that it is acidified. So we cannot use this one because we don't have that extra hydrogen. Okay. So going back here, we out of our other two, water won over potassium. So water, when it gets reduced, will make hydrogen, H2. So at the cathode, it's going to make hydrogen, H2. And so the answer would be C. Okay, that was better than 86. Whew. Which of the following could be titrated using acidified? In this case, we do have that extra H, acidified permanganate ions. So we want something that will react spontaneously, because if it doesn't react spontaneously, it's not like we're going to be dripping things out of our burette and, you know, hooking it up to an electrode, or sorry, a power supply. That just doesn't make any sense, right? So this has to be spontaneous. So let's go look up acidified MnO4, and I'm just going to jot down that our possibilities are Mg2 plus, IO3 minus, SO4 3 minus, that should say 2 minus. Typo. Hello, pen, why are you not working? Other pen. Other pen. Should be typo. My own future reference. Fix it. Okay, and H2O2. All right, to our chart. Acidified permanganate is up near the top. Acidified permanganate is up here somewhere. Yep, there it is. Permanganate. And there's our hydrogen. So it's going to be spontaneous with just about everything on the right-hand side. I know it's not going to be magnesium 2 plus because magnesium 2 plus is on the left-hand side, and you cannot have an oxidizing agent reacting with another oxidizing agent. It needs a reducing agent. So let's go to IO3 minus. See if we can find that. Again, I'm guessing it's near the top of the table. The top of the table has all the things with oxygens and complicated formulas. IO3 minus, oh, there it is. And guess what? It is also a an oxidizing agent. So we cannot react that with MnO4 because we can't have two oxidizing agents. How about SO4 2-? Oh my gosh, of all the things, that's one where it would not be spontaneous with SO4 as a reducing agent. So not that one. And that leaves, last but not least, H2O2. Let's hope for the best. Hope we find H2O2 over on the right-hand side. La, 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 la. Oh, there it is. Huzzah. And that, there's our permanganate. And there's our H2O2. I have an oxidizing agent. I have a reducing agent. And I've got a positive voltage for that thing. You can see it goes downhill, but if you didn't have the downhill, you could use the fact that E naught of reduction is positive 1.51 and E naught of the oxidation of H2O2 is negative 0.70 volts. And so E naught of the cell would be positive 1.51 plus negative 0.70. And I don't know what that gives us, but it definitely gives us a positive value, and therefore it is spontaneous. So if it asked you to do a calculation to prove that, you could do that calculation finding the E naught of the cell. Okay. That was 88, 89. What is the oxide? What a compound is that? Oh my God. Okay, we need boron in this borosite. Okay, so we have 3 magnesium. We have 7 boron. We have 13 oxygen. And we have 1 chloride equals, and there's no charge at the top, so it's equal to 0. Magnesium is an it's an alkaline earth. Alkaline earth in compounds are always +2. So 3 times +2. Boron is the one we don't know, so we're just going to leave it as 7 borons. 13 times oxygen. Oxygen is always -2, except for some rare circumstances that you won't come across very often. So that's 13 times -2. And chloride is almost always -1. It can have a variety of different charges, but if they're asking you to find boron, you have to assume that the oxygen and the chloride have the most common charge possible, and that is, or common oxidation state possible, and that is -1. So that's plus -1 equals 0. And I'm going to do this in the long form. 6 plus 7b minus 26 minus 1 equals 0. And so that's -20 minus 1 is -21. 7b equals 0. And so 7b is equal to 21. And so b is equal to 3. +3. E. So that one's just a little ugly, requires a lot of math, but easy math. So there we are. An equation for the rusting of iron is shown below. Which of the following is false? This is a redox reaction. Well, remember, we're looking for something that is untrue. Is it true that it is a redox reaction? Yes, it is. Iron goes from being 0, oxygen from being 0. Iron over here, that doesn't look like a correct formula. But you know, maybe it is. I don't know. I'm going to put a big star and a question mark beside this one because I typed this in from a source, and I'm just going to go back to the original source and make sure that that's not supposed to be Fe2O3. Let's assume that's supposed to be Fe2O3 because I've never seen such a thing as FeO3. Fe2O3. There we go. Typo. And this would be then, if this was the correct formula, we have Fe being 3 plus and oxygen being 2 minus. O3 is the oxidizing agent. Maybe that should say O2. O2, typo. Because O3 is part of a compound, makes me unhappy. Oxygen is oxidized to O2 minus. We know that that one is false because when O2 goes to O2 minus, it has gained electrons, and therefore that is reduction, not oxidation. So C is false. Metallic iron is the reducing agent. Yes, if it reduced the oxygen. So metallic iron is the reducing agent, and I'm going to assume that that was O2. It should be a 2. O2 is the oxidizing agent. Yes, because it's getting reduced. So everything is true except for C. We're going all the way to 94. So let's see, in which of the following chemical changes will the oxidation number change by +3? Well, obviously not this one. It went by -1, 3 to negative, 3 plus to 2 plus. So we have MnO2, I have Mn plus 2O equals 0. It's like 20, but it's not, it's 2O. So Mn plus -4 equals 0. And so Mn is equal to +4. I have a tendency to write all these things out because I tend to make stupid mistakes if I try and like do it like this. I go like, oh, that's -8 and I've got one negative there, so that's +7. And yes, I did it correctly that time, but sometimes I don't, right? So to be safe, I might write it out unless I'm good at doing them in my head. So that is a change of +3 +4 to +7. So that's going to be our answer there. Let's just double check these other ones. Cl plus O equals -1. Cl minus 2 equals -1. Cl equals negative, +1. Cl plus 2O equals -1. Cl plus 2 times -2 is -1. Cl minus 4 equals -1. And so Cl is equal to +3. And so that is a change of +2, which is not what we wanted. And yeah, this one looks way bigger than +3. So we'll just keep that there. Okay. Identify the oxidizing agent in this reaction. When you're asked to identify the oxidizing agent, you're going to assume that you're looking in the reactants, okay? So the oxidizing agent gets reduced. And we go from, let's see, iron lost electrons. So it is being oxidized. And, oh yeah. This guy here gained electrons. So that is reduction. And yeah, that looks good. So if this has been reduced, then our oxidizing agent is the one that got reduced. So that would be our Ce4 plus. There we go. 93 and 94. Okay, so we have inert electrodes. We have copper 2 iodide. So we have Cu2 plus in here. And we have I minus in here. And it's aqueous. So we also have water in here. And our electrons are going this way. So this is our anode. No, what am I saying? That's our cathode. Oh, cathode. And that is our anode. Which reaction occurs at the cathode? So we need something that can be reduced. because reduction always takes place at the cathode and not paired. C-A-R-E-D, or both consonants. There we go. Okay. So something that can be reduced at the cathode. Well, always water, if it's there, is an option. Cu2 plus can get reduced to Cu0. I minus reduction is gaining electrons. I minus cannot gain another electron, right? This is just not a happening thing, right? Have you ever seen such a beast? No. It would have to go into, once you've filled up iodide's outer shell, if you tried to put in another electron, it would have to go further from the nucleus. And so it's not actually that attracted to iodine once it's, or iodide once it's got a full shell. All right, what is the reduction potential of water? I think it's 0.4 something. Let's look. Water. Negative 0.41. And copper, reduction potential of copper. We have one here. We have one here. Copper 2 plus, copper 2 plus. Which one would we choose? Would we choose 0.34 volts? Or would we choose 0.15 volts? Always choose the more positive option or the less negative option. So out of all three of those, this is the most positive. And so that would be our reaction, copper 2 plus going to copper solid. All right. So at the cathode, it's going to be copper 2 plus going to copper solid, and that is B. 94, what happens to I minus concentration in the operating cell? Well, that's going to depend on whether I minus is actually the thing reacting. So at our anode, we have to look at our possible oxidations. And of course, water is always an option. We have an inert electrode, so we don't have to worry about whether the electrode is going to react. We have I minus, so we're really comparing water and iodide, and we're going to look at their oxidation potentials. Got a booklet. Water being oxidized is up here. This is water. And its oxidation potential, ooh, if I just erase this, it'll still be there, is negative 0.80 volts. 82 volts, sorry. That's the oxidation potential of water. The oxidation potential of iodide. Iodide, oh, there it is. And its oxidation potential is negative 0.54 volts. And so who is less negative out of those two? And we're looking for the less negative one or the more positive one. And so this is less negative, therefore that is the preferred oxidation. And so I will be reacting, and so it's going to be going that way and turning into I2, so the concentration of I will drop. So concentration of I minus decreases overall because we're using it up. I see a D on the answer key for number, that's probably wrong. I feel like that has to be wrong. Do you guys agree with me that D is not correct? for 93. Like we looked at the reduction potential of copper and of water, and copper was better getting reduced. Do you agree? Okay, so the answer key for this one is incorrect. So I will make that change. That is it for questions that I think people have asked me. Is there anything else that you would like to look at? Any of the written response or anything? Going. How are we feeling about our upcoming test on Friday? Okie dokie-ish? Nobody's willing to commit. That's okay. All right. If there's no other questions, shall we call it a day then? And you guys can go off and study and work on things. How long is the test? It will be designed for an hour and 15-minute class. And it will have 24 multiple choice questions and 16 marks in the free response type questions. I'll call them written response because that's what they're called in the regular thing. So 24 multiple choice, 16 marks in the written response for a grand total of 40 marks. Anything else you'd like to know? Or am I going to post the videos that you recorded yesterday and today? I'm definitely going to post the one I did today. Is the written similar to the written in the review? It should be. Yep. None of the gray questions will show up on the test. No, they will not. Okay, so I'm going to post today's video for sure. Yesterday's video, I have to see if it actually worked. If I closed my computer before it had finished processing, I might be out of luck. So yeah, if it didn't work, I'll try to just post my scribblings that were all over this document here. Okay. Anything else? Nothing else? You can always email me if you have a question in between now and Friday. What time are we meeting on Friday? At 11. Okay, so I will see you at 11 on Friday. And we will write this test and get it done and dusted so that we can start finishing up reaction rates when we're here on Monday. All right. Have yourselves a great rest of the week, and I will see you Friday. You are very welcome. Okay, more. Stop recording. Stop recording. Yes.